Okay, it looks like the audio is working. So we're going to go over all the back-end LabVIEW stuff on how to operate the applet instrument. So off camera, the first things that we did was turn on two pieces of hardware that this connects to, specifically the K-Cube and the Wasatch probe. So the first thing to know for sure is that we do not have either of these softwares open. So Enlighten is the one that opens the spectrometer. That needs to be closed and shut down. The other one is this KLC software. Sometimes when there's problems, it's good to open this piece of software up and try to connect to the instrument. So here, when you see these kind of options, that means you can connect to it, that the driver is available for Windows. And the only way that I've been able to really get it to work with LabVIEW consistently is if you hit disconnect here. And what you'll see is that it's gone completely. And at this point, we should be able to reliably connect to it through the LabVIEW interface. So the place to find it is if you right click on the LabVIEW icon. It's usually the most recent version is one of these pinned ones up here. So that's this one right here, right? This VO2, which we already have open, which is this piece of software here. So if I click run, knowing that those things are open, it takes a second to initialize and make the connections with those instruments. And these green lights here will, do you guys see do you see a cursor over there? You don't see a cursor. Maybe what I'll do is I'll just move over here so that you can see it on my screen as well. And then can I trade spots with somebody? Sorry. Can you see okay from there?
Yeah.
Yeah, so I look for these green lights over here to make sure that I've successfully initialized the connection. Right now the laser's off, so this is the raw pattern that the detector is going to pick up in the absence of any light that it's collecting. So in order to account for this, you can acquire a dark spectrum. So this is saved in memory, and you can subtract it away so that all that remains is the noise on the detector. This is dependent on the exposure time. So if I change the exposure time here to say like 200, what you'll see is that the dark spectrum is back because it doesn't fully subtract it. So what you have to do is acquire a new one and subtract it away. You should be able to just acquire it when it changes. So if I go to like 400 milliseconds, I should be able to acquire it here and then have it correct it. And I think that this is automatically output to another file as well, or it's automatically subtracted from the spectrum when something is saved. So as important as turning on the software is, turning off the software is important. You need to use this shutdown software button here. And what that does is it ensures that all the different pieces of hardware connected to LabVIEW is disconnected properly so that it can be connected to by LabVIEW itself later or through their native softwares like the KLC software and the Wasatch probe software. So if I hit shut down, it takes a second, but then it's totally disconnected. And now I could restart this program if I wanted to, or connect to it with the other ones. So going into the back panel on this, LabVIEW typically runs left to right, but it's controlled by wires in terms of the information flow. So in terms of organization and overall runtime, we start with the buttons on the left-hand side. So these are all the actual buttons that you can interface with on the front panel. So you can see like this is the actual tab control. This is like a root path here. And keeping all the buttons here is really nice to stay organized. And the way that you access the values in here is through local variables. So you can make a local variable on any of these by right-clicking them and then go to create
Under restrict.
Yeah, local variable. So I can drop that. The nice thing about this is the value is always available either to be written into the way that the direction is right here. So if the connecting terminal is on the left-hand side of that, I mean, information is flowing into it. So this is like an indicator, but you can change it to read, which makes it like more of a control where you can take the information out of this variable. It's really nice to have that flexibility because if I just have the variable sitting somewhere in the loop and I want to like write to it, but it's a control, then I'm not going to be able to do that because it will only let you read information or write information, but not both. The local variables give you that flexibility to do either of those. So this is my preferred way of organizing everything. And then you can see all of your buttons here. And Sarah's done a nice job of kind of organizing them here. So all the dark spectrum buttons, all the saving controls, and all that stuff is neatly packaged up into one space. So overall, there's 4 sections in the sequence structure. So a sequence structure will take this frame over here, execute everything in it, and then once it's done, move into the next frame and the next frame and the next frame after that. So the first one is all buttons, but it has this thing here, which I want to execute before anything happens. And all this does is it refers to this VI and it reinitializes every button to its default setting. So nothing from the previous like time that you ran the software will carry over into the current session. And this is nice because if you're programming, sometimes like if something carries over from the last session into the current session, it could cause errors. If you have like true values that should be false or false values that could be true, and it's a huge nightmare for troubleshooting. So I found it to be really helpful to start from a clean slate and define all of your variables from some sort of like default initialization and then go from there. So that is the very first thing that we do. And if you want something to be a certain value when you initialize the software, for instance, I want this to be always disabled. What you can do is set it to the value when it's not running that you want it to be when it starts up. Then you right click it and then you go to data operations and then make current value default and then save it. I'm not going to do that because I think we're happy with the default values. So if I run this right now, the default value is to have this spectrometer enabled so that right when you boot it up, it's reading spectra out immediately. But if you didn't want to do that, then you could click this and run it. So I'll leave it disabled right now. And when I click the run button, you'll see that it turns to enabled right away because that's the default value. And the reason it switches to that is that very first thing that runs.
Okay. Can I ask something?
Yep.
I always copy and paste this here, this VLI, and then the VLI. How do we write it from the scratch?
I have no idea. That's exactly how I did it the first time. I went online and I downloaded some person's like VI and then I copied and pasted it into mine. So this is a property node and the property is this VI. And I'm sure you can find this down here under default values, but I don't know where to find this VI.
Yeah, that one.
Which one is a property node and what is
this
a
one
property
here?
Node? Wait, sorry. Oh.
Yeah, so a property node is this.
This thing.
Yeah.
Okay.
So you could go to what is it called? The view quick drop palette, and then probably type in this VI. Yeah, and it will drop that. But I don't know where in the menus to find it.
Okay, yeah, I went through the menu. I never found it.
Yeah.
Okay.
So then I can probably go like this and go to create property for VI class where it says default.
Oh.
Or somewhere here. I actually don't even see it.
Would be under toolbar.
Yeah, it should be under default method. So, oh, it's a method.
Mhm.
And then default
Default
values,
values,
reinitialize
oh,
alt.
okay.
Yeah, so then
And
it'd be under
then-
here. And then this closes the reference, I believe.
Okay.
So that's how you make that. I hope you never have to do that in your life. I would just copy and paste it right from another VI. It's the way that I always program. So then in principle, there's three main things that are happening in this VI, and they happen in sequence. So that is, first, you initialize your connection to all the different hardwares. And then once you've connected to all the different pieces of hardware, then you go into runtime, where you're looping indefinitely and waiting for user input. And then the last piece of user input is, I don't want to use this software anymore, and you want to shut down all the hardware. So then that's the last loop over here. It's hardware shutdown. So
So it's like the first column, just initialize, the second, make the connection with the hardware pieces, the third is the user inputs and variables, and the last one is shut everything down.
Yep. And it always works that way. So I will show the very most basic way to connect to these. I think the K-Cube probably has the simplest connection here. Yeah. Okay. So the way that this works is we have an initialization for the K-Cube. And this is a sub VI. So if you double click it, it'll bring up the sub VI, and then I can go into its back panel and it shows this. So these are pieces of software that are written by Thorlabs to control the instruments. So what we've done here is kind of piece all of those different small subroutines that they've written into one program that initializes all the settings that we're interested in. So there's probably like, I don't know, there's like 40 or 50 or 100 different things that you could do with this. And all we wanted to do was turn it on and like set the voltage and keep it there. So surprisingly simple things are complicated to do because they try and pack so much functionality into one thing. It's always worth it to try and find like the most simple, smallest low level VIs that you can find from the manufacturer and piece those together in the order that makes sense for what you're doing. So for us, basically what that is first it's a list. So it lists the communication ports that K-Cubes take up on the computer. So we have just one, so it's always the same communication port. But if we had like 5 K-Cubes connected to the computer, this would output a list of 5 different K-Cubes. And what we would do is choose the K-Cube that we want. Since we only ever have one, it's always the 0th element of that list. So we take that and put it into this open sub VI. The open sub VI outputs so it makes the serial connection and it outputs this handle out. So the handle out is a 0 the first time that it runs, and it's a -1 if there's an error. So if you see a -1, then you're going to have a problem. You're probably going to need to shut down all the software. I would connect to it in the way that I did before, where you connect to it with the KLC software with LabVIEW closed, and then you disconnect from it, and then you close the connection. Restart doing that with LabVIEW. Then once you've initialized it, you want to open the port. Then this one gets the current voltage. This one gets the frequency. So typically we run this at a constant frequency all the time. We just forget about it, but it's consistent and it's a number that we need to know. And then the last one is enable. So basically we make the connection to it, figure out what all the settings are, and then we enable it so that it's working with those settings. The flow of information can be controlled with error bars. So these error wires are typically connected to the bottom left and right as the input and output. And if you string the order of things you want to execute along an error wire, then that's the easiest way to control the order of execution in LabVIEW, because these things can be organized all over the place. I can do this and that and that. And, you know, it looks really terrible, but it's still going to work because the error bars are going in the correct order of execution. So I'm going to go ahead and undo that because it was just absolutely rude to do. So I will close that. The sub VI is nice because if you click on any of these things, so we're interested in having the voltage, the frequency, the handle out, and this option to know if it's actually been opened properly in the main VI. And those are connected through these wiring terminals in the top right of the sub VI, as well as the error in and error out.
What was handle out?
This is a code that the software outputs to tell you if a driver connection to the K-Cube hardware was done successfully. So if there was an error in opening that and connecting to it in LabVIEW, the handle out is a -1. If it's successful, then it gives you a 0 the first time. Yeah. And then if you connect to it again, it counts. So 1, 2, 3, 4, all the way up to however many times you're turning on and off the software. And that's it. So you can use this for like error case. So like say there was an error in the connection and there was a -1 out, you could have some condition further down the line that checks to see if it's -1, and then it will shut down the software or like take some other measure to try and fix that.
So in the front diagram, we have handle out in the extras. So whenever something comes up with the instrument and with the interface that I don't know what's happening, I just go to extras and see what's the handle out here. Now it's 2, so it's going to be fine.
Yeah. Yeah, so you'll see if I hit run again, it'll open here, hopefully. Yeah, and now it's 3. So it continues to like go up and up and up. So that's what we always do, is we initialize the hardware in this kind of way, and then we take information out of it that we're interested in. So like the frequency, the K-Cube voltage. So this one is like here, this is the slider, it'll output to there. And then like the handle out, that'll, oops. And then that'll output directly to here what we were checking before. We do that for right now, 2 pieces of hardware. So the other one is the Wasatch system. And this one's a little bit more complicated.
The thing is right behind your monitor, the whatever thing.
Oh, yeah.
So you're looking for the spring and thing. The spring and bolts.
This boy?
Yeah, this. The bouncy boy. Yeah.
The what?
That's a good name. It's a good name as any. So here is the initialization for the Wasatch spectrometer. This one has significantly lower level initializations. So I don't think we actually wrote a lot of this. I think what this was is we took this and we started removing functionality from it.
Wait, what do you mean? We added some functionalities to it.
Oh, okay.
Yeah, so these parts were part of the template that we used until the serial number and model.
Right.
And then until the actual frames.
Okay, then what we were interested in is this stuff here, right?
Yeah.
So we wanted to know the pixels.
Yeah.
We wanted to know the wavelengths that are coming out of it. And then over here is the conversion using 798 0.98. I don't, oh, this is the calibration.
Yes.
Yeah, so we
yeah.
read these calibration constants out of it.
Yeah.
We use that to get the wavelengths, and we use 785 to output the wave numbers.
Did you download this from Wasatch though, like this part?
So
what you
whenever
mean?
you get any instrument and you want to install it into your LabVIEW, you get some drivers and you get a VI tree, which includes all the functions that you will have in that instrument, and you can add anything you want. And also you have some templates, like some demo, it's called differently. So one of them is just open, like KQ, something like that, or open Wasatch. And it is very simple just to start working with it. So you just take the first part and add the other property node that you want for initializing and working with the instrument later.
This is the spectrometer, Wasatch spectrometer program.
Yeah.
Yeah. So this is the saving path.
Yes.
And one thing that we put in right at the end is our integration time that we're interested in. So by default, this value is 100 milliseconds, but then you can change that to whatever you want anytime that you want. And then excitation nanometers, this tells you the wavelength that it thinks is being used for excitation. Yeah. And this one's 785.
Yes.
For the default integration time, can we go lower than 100?
Yeah. Yeah, you would just have to change that. So we would go, this is the sub VI. Anytime I'm closing a sub VI and I've like kind of clicked around in it, but I don't want to do anything, I just defer the decision. I don't deal with it. So what you would have to do is over here in the front panel, you would change this to some other number, and then you would data operations make current default. It's not really necessary though, because this is just to get the instrument going. And then once it's running, you can change the integration time to be whatever you want. But for instance, if like it was running at 10 milliseconds and I'm not really going to get a good signal with just about anything by default all the time, then it's not really useful to have that value in there. I thought 100 was like good enough where you'll see data coming in really, really quickly, and you should be able to see some kind of Raman spectrum if the laser power is high enough. But this is all just preference at this point. So the reason the sub VIs are nice is if I look at this, I'm like, okay, this is the initialization for the spectrometer. And then down here is the initialization for the K-cube. And all the details that I just showed you in the sub VIs here are not really important for you to understand how the overall software works. And it's kind of hidden in the background because all I know is that this thing here turns on the K-cube and gives me some settings about what they are when it boots up. And same thing for the spectrometer. And that's it. So that's the hardware initialization. Sometimes we do a little bit of data initialization as well. So here we initialize the dark spectrum to a value of 0, which it should be. So you want to collect a new dark spectrum every time. And once everything is open, once all of this is done, it'll move from the hardware initialization to the program runtime. So the program runtime is where everything is initialized and the program is waiting for user input. So it'll be running in some sort of default state. Every piece of hardware will be running in at least one loop, usually one loop. So over here, we have the Wasatch Pro runtime loop. So this thing will be running forever until we tell it to stop running. So we have a stop button here, which I've pointed to, which is the shutdown software button. And this one will shut down the Wasatch runtime loop, which is shut down by passing a true value into this little stop sign, as well as in this K-cube operations one. And we also have one that generates sine waves, and then another one that handles all the file saving as well. So that one button basically triggers an event in every single while loop that's in the program runtime frame to stop running. And your program will not run unless you've figured out a way to stop a while loop, or else you'll get into an infinite loop and you'll never be able to stop the program and it can go out of control. So that's basically the principle here, is that we have a while loop for each hardware that's connected, at least, and then typically more while loops. So in the default case, what would be happening here, and not doing any file saving or anything, is that we initialize the spectrometer to run, and then the program runtime loop is every time there is a new spectrum that comes in, it will display it in this window and update it. And then when we click shut down software, what will happen is it will initialize this event, which will hit the stop button here and in all the parallel running while loops, and send it into the final frame, which is hardware shutdown. So this one here shuts down the spectrometer. And then this one here shuts down the K-cube. So that's basically it about the overall flow of basically turning on the program, waiting for user input, and then shutting everything down properly. Is there any questions about just that before I actually get into the details of the way that the program responds to user input? Everything's good.
Basically.
Yeah.
Sorry. Could you please put that in the middle?
I tried to clean everything, but it's, yeah, cool, thank you.
Yeah, so you can automatically clean things with this broom, but it's gonna just cause huge problems.
Yeah.
Yeah. So I'm going to start talking about the runtime in this most simple way possible. I think that the most simplest one is the K-cube operation. So once we've reached this while loop here, essentially what we're doing is we're waiting for user input. So these while loops will run as fast as they can unless you tell them not to. So these timers here, this is a wait timer. The input is in milliseconds, and this tells it to wait 1 millisecond before it moves on to the next loop. So running at 1,000 loops per second is pretty reasonable. If you let it just run as fast as it can, it'll do like a couple 100,000 million, maybe 10 million loops per second. And that's just going to put a lot of strain on the processor very unnecessarily. Because if it's waiting for me to like change a value in the K-cube, it doesn't need to do that in nanoseconds. Like it's fine if it waits a millisecond to do that.
How did you decide 1 millisecond?
So you got to figure out what your rate determining step is. And in this case, nothing is going to run slower than the acquisition time for a spectrum. And
As in, like, the spectrometer is the rate limiting step. Okay.
yeah, so like 10 milliseconds is like the fastest that you're ever going to acquire a spectrum. I think the user manual says 40 milliseconds is the minimum amount of time that you should be collecting light for a spectrum. So you can just be, it's nice to be like at least 10 times faster than that on the wait timer. 1 millisecond tends to work well. It really depends on the thing that you're looking for too. So like if it's like a stage that I'm trying to move, then a millisecond or maybe even less than a millisecond may be necessary because you want it to respond as quick as possible. But if it's something like updating a file name, like you don't need to respond in 1 millisecond to update the file name. So you can have this wait 100 milliseconds and that'll still, to your eyeballs, look instantaneous. But in the software, that loop runs 100 times slower. So that tends to save a lot of strain that you would put on the processor.
So with our spectrometer, minimum 40 milliseconds before it's going to output. Okay. So it means that every 40 milliseconds it's outputting a spectrum. It's updating. Okay.
So this is
like
this is the minimum time it thinks it's going to take
but it
to
might take
output.
longer.
It might take longer, but it could also take less time. Like I think you can actually run it at 10 milliseconds. Like this spectrometer, the Princeton Instruments one, you can output a spectrum every 10 microseconds.
Wow.
Yeah.
Is the CCD different? Is it like
it's cooled.
Cooled. Okay.
Yeah, it's cooled, which is really helpful. The cooling is actually more helpful for longer acquisition times because when it gets colder, you get less buildup of like a baseline noise, which is temperature dependent.
Yeah.
So this system, the PI system, is just a lot better in basically every single way. But there's also a lot more room for error and a lot more variability in the experiment. So I actually really like the Wasatch system once the software works and you can connect to it, because you can't move the grading and there's just like there's just a lot fewer things that you can mess with. So like over a course of time, you just get a lot more consistency by default between your data.
So in terms of LabVIEW programming or in general, for example, if you use the instrument default, the instrument is still you're running into problems due to all the complexity it has, or is mostly for the programming LabVIEW?
Yeah, so like the more features a spectrometer has, the more complicated it is to like run in LabVIEW.
Okay.
So I could set it up so that the PI spectrometer is as simple as the Wasatch spectrometer by not giving you access to all the features in the LabVIEW interface that it's actually capable of changing.
Mm-hmm.
So I could choose to not integrate the different grading control into LabVIEW, or I could specify that I want the wavelength, the center wavelength, to always be fixed at exactly the same place, which are things that are just like fixed in the hardware of the Wasatch system, but are flexible for changing in the Princeton Instrument system.
So if we didn't have, this is kind of the most complicated part to me. If we didn't have this wait set time, everything would everything just run a lot slower because it's just going unnecessarily quickly?
Yeah, I can show you
Yeah,
here.
I love that.
Yeah, so what I'm gonna do here is I'm going to just set up a while loop. I'm going to create a control, which is just a stop button. And when I click this, it's going to stop. And then over here is the loop counter. So I'll create an indicator here. So if I run this, basically what's going to happen is every time the loop executes, this number will go up. So this is the most simple loop that you can possibly do. If I can get this running. So if I run this, yeah, you can see how crazy that is. I should actually make this bigger.
So I guess, but like with respect to the rest of the software, it just slows things down because that's just moving unnecessarily quickly.
Yeah, okay. Exactly. So then all you need to do is input, so it's under timing, and then go to wait. Yeah. And then I can change this to a constant. So let's say I make this 100 milliseconds. Then this will update at a rate of 10 per second.
Okay, nice.
Which is fast. But depending on what you want to do, this may be too slow. So you need to be careful about the actual value that you put into here.
Thanks.
Yeah. So the core of any of these while loops is an event structure. So event structures are waiting for user input. So the default case is this timeout case. And there's a little like button over here or a little input on the top left, which is like the event timeout timer. So instead of saying 1 millisecond over here, I could say input 1 millisecond into this event structure, which says like, wait 1 millisecond for input. And then if there's no input, run the timeout structure. I prefer to separate them because it gives you a lot more control. But in general, basically, I say if there's no user input after 0 milliseconds, which is immediate, then just run the timeout case. So in this case, the timeout case does nothing. All we're doing is passing the error bar through here to continue the flow of error. By default, there's nothing attached to this, and it'll be a value of -1 instead of 0. So you need to wire the 0 to here because when it's -1, that's a special case where it will wait indefinitely for user input. And what that does is typically lock up the entire user interface. So definitely remember to do that. That's been the source of like a lot of problems for me, is that a while loop will get stuck waiting over here and it will affect other loops that are happening in the software. So what you want to do is ensure that all these loops are running at the same time in parallel. So these are completely uncontrolled loops. They're all running by themselves independently, and you want to make sure that remains the case. So that's the most flexible way to do the programming, I think. So there is one case where this will do something. So it is an event that happens based on the K cube voltage, which is this slider bar over here. So what that loop is doing is it's waiting for some change in value here. So when it finds that there is a change in that value, what it does is it takes that new value and it inputs this into the set voltage sub VI. So this will set the new value to the K cube. And over here, show voltage. I think this is just a check for you right now. That could probably be in extras, but it's just there. The K cube is a little bit sketchy in terms of how it communicates with LabVIEW.
Extremely sketchy.
Yeah.
You were
So it's
with it.
yeah,
Actually.
it's the worst one for sure. So sometimes it's nice to have that additional check there.
It's a big plus.
Yeah. So then if I come here and I run the software, what would be happening is right now we are in the timeout case, which is this one. And then if I were to change this value to say here, then it will flip over to there, set the new voltage, and then the next time it loops around, it's waiting for input again, and we'll be back at the timeout. So then I will go back to the default.
So after 0 seconds of no input, it's timing out. Okay.
Yeah. So it's like every millisecond, if you're like
The
making a
next
change within
yeah.
within that millisecond window, then it will trigger that event in the loop. And that's the basic principle for pretty much how every single button here works. So for instance, what's happening up here in this runtime loop is when it's timed out, the first thing that it checks is for this enable spec, which is this button. So by default, this is enabled. So this value is true usually. If the value is false, which is the case right here, then what's going to happen is it will disable these two buttons, the acquire spectrum and the dark spectrum button, because you can't do anything. The spectrometer is not enabled, so you're not going to try and acquire anything. And then as soon as I re-enable it, what it's going to do is make sure that these buttons are enabled. it will get a spectrum from the spectrometer and has a couple things here. So the first thing it will check for is if subtract dark spec is enabled over here. So if it is enabled, what it will do is subtract the dark spectrum from the spectrum it just read and pass that out to the next processing. If it's false, then it won't do anything. If I've clicked acquire dark spectrum, this will be true, and it will feed this spectrum that it just captured into a variable called dark spec. And this is sitting in the extras panel over here. So this is where we actually save our dark spectrum. So if I enable the spectrometer here, you'll see that these buttons are back. And if I click acquire dark spectrum, so I'll be clear about this, dark spec is an uninitialized array. And what we want to do is fill this with the spectrum when everything is off. So I click this, and then now we have a dark spectrum in this variable. Right now, this is false. So the dark spectrum is actually not being subtracted from the display. But if I click true, then it will subtract it. So basically, when this is enabled here, it will always subtract that before it goes to the display.
Sorry. I click.
Yep.
Oh boy. Yep, there's... Okay.
What other cases are we here? Yeah, so this is the situation most of the time that it's going to be running in is the timeout. So that just by default is seeing if the spectrometer is on and will just continue to stream data out of the spectrometer to do anything with. So the first thing obviously is sending it into the display. So here we have the wavelengths that we got from the initialization, and we combine that in a cluster with the spectrum that's read out and send it into the display, which is this guy. We also feed that into a variable called spectrum, which is this one. And you can see it changing because the spectrum is always changing. This is actually a 1D array, but it's just been truncated because you don't need to see all of it all the time. And then into this transposed array with wave numbers, which is used maybe down the line for something. So the other case for the spectrometer is if you want to change any settings. And pretty much the only setting that you can change is the exposure time or the integration time. So this case here responds to when there is a value change here. So if I change this to 200, what will happen is this will execute one time, and then the new value of integration time right here is fed into this property node. So the property node has a link from the initialization here that tells you what the connection code is. I actually don't exactly know what this is, a .NET connection reference. So we send that into a property node, and then the property that we're trying to change is this integration time. And that's it. So this executes one time, and then it's back to the timeout case. So that's why you'll see if I change this back to 100, it will pause the spectrometer for a second because it's not grabbing information from it anymore. It'll change the setting, and then it will go back to collecting the data. So that's the basic operation of how the two pieces of hardware work. Is there any questions about that yet?
Actually, those things that we put here, the transpose array and also the spectrum is just for checking. So
Yeah.
at the end of the day, I will remove all of them.
Yeah.
So they're just there to make sure that they're getting the spectrum.
I'm going
Is that's just because like LabVIEW likes to make its arrays like in this way, right? Not this way. Is that why?
Yeah. So my idea was that instead of having a driver to get the data from somewhere and just put that in another loop that we have, we can just have a local variable like transpose data and then just get it from here to the others. But we realized that this is a better way to have a driver to write and read the driver like get data into other loops that we have. So it's just for checking to make sure that because the way I realized from Luke that it's the best way to write in LabVIEW is that to check everything that is running. So even though some of the variables are not worthwhile anymore, they will help us for like checking that everything is running. Yeah.
Okay, I'm gonna pause right here for a second. Okay, so we left off talking about how each individual piece of hardware runs in its own loop with its own controls. And we don't necessarily want them to just run off by themselves. We want them to communicate with each other. So although they run in separate loops, we need to be able to have them talk to each other. The first thing that happens, and I think the most important thing, is that this Wasatch Pro 785 runtime loop, its purpose is to retrieve data from the spectrometer, and that's all it does. So it will retrieve data, it will display it, it will give you the option of removing a dark spectrum that's acquired, and that's pretty much it. So it just loops indefinitely, grabbing spectra, and then sometimes if you change a setting, the integration time, it will make that change in the settings. But that's pretty much it. So this data collection loop is connected to a loop that's running in parallel. So this is a file saving loop. And they're connected by this channel writer. So a channel writer you can think of as like a tunnel between two different loops, where this loop will output the data from the spectrometer and run along here and pass it into this second loop. This loop is dedicated to file saving, and there's a couple different modes in here. So there's the applet mode, there's the Raman classic mode, and the SERDS mode as well. So we will start with the Raman classic mode because I think it's the easiest to understand. But before we go into the details of that, I'll show you how to actually make these channel writers. So you can make them by taking data. So this is coming right from the property mode from the spectrometer where it says get spectrum. So we're processing on this and we want to pass that directly into the next loop. So if you right click on the wire, you can go to create channel writer. And it's going to give you multiple options here. Typically what we do is we stream it and just write. So the default settings tend to work fine. And what this basically creates is a queue. So you'll see you have a bunch of data streaming into here from one while loop, and then it will go in that order to the second while loop. So it's a first in, first out style of passing data. So if you click OK, it takes a second, and then there it is. And then you can wire this directly into another loop like this. So the way that you actually extract that data is to create a channel reader. So once you've connected that to the consumer loop, So the top one here is a producer loop because it's producing the data. This bottom one here is a consumer loop. It's consuming the data. We want to read the data that's being passed to it from the loop up top. So if you right click it, you can create a channel reader. And I use the same settings here, but it's just read. Typically, you want to read them one at a time. You don't want to spit out a ton of them. You want to take one spectrum as it comes, do something with it, wait for the next spectrum, do something with that. And then we can put that here. It doesn't like having multiple readers. I mean, you can read it one time and do multiple things with the data. But the important thing here is a couple settings that you actually get from the channel reader. So one thing here is the timeout in milliseconds. So this is like it's like the event structure where you have to specify a time, and by default, -1 is wired into this slot here. And that means that it will wait indefinitely for data. I find that usually like gives hiccups in the code and doesn't work so well. And it's better to have a default case in the loop that just does nothing until some data comes in. So I will set this to 0 usually, which means that like if this loop runs and there's no data there, then it will just go and loop again. And it will do that until it has some data passed to it. And then once it determines there's some data, then it will do something. So you can pass out a Boolean that says, did this time out? One that says, do I have a valid element that's coming out of here? And this one down here, last element, tells you if you're at the last data element in your queue. You can output the count. I've never really used that. Most of the time, I just wire a 0 into here, and then I just send out the data. Sometimes I use this element valid. That can be helpful, but usually don't. Okay. So in the case that you click save data, well, this is always streaming. This is always streaming data. Every spectrum gets streamed into this file saving loop. So here in this case, we're not actually taking any data from this channel writer. We have data that is being sent into a local variable here. So this is transposed array. Every spectrum that comes in is this transposed array, and this loop here basically waits for you to click acquire. And it will be in this Raman classic case if you have it clicked over here. So as soon as you click acquire, it will come in here. It'll take that transposed array and write it to a spreadsheet with all these naming properties. And if it's false, then it does nothing. So this will just loop indefinitely, waiting for you to save a file. The next one is SERDS. So this one actually takes data from this channel writer. So we come in here. First thing that we do is yeah, I see how this works. This is like, I like this. Okay, so you click, if acquire is hold on, how does this work? You click max min. So the data is streamed in here, and then you set the minimum voltage, and then over here, the spectrum is put into a file. So does this actually work?
Yeah.
It does. Because you're taking a spectrum that's taken before you change the voltage setting, right?
Yeah, I see that right now.
And then it puts that in here. Like it will save 2 spectra every time, but if it's the right 2 spectra is the thing.
I see.
Yeah.
Mm-hmm.
So like the first step that needs to happen is you need to go to the minimum K cube voltage, and then you take a spectrum, and then you change the voltage, and then you take another spectrum.
Yeah.
So that needs to be the order with that. So I think that needs to be modified. But the idea here is basically you take one spectrum and then you change the K cube voltage and you save another one. So here you have the max voltage, and then you take a spectrum and save it. Mm-hmm. And then in the other case, you take the minimum voltage and do the same thing. So you have 2 different files for certs.
So we click one acquire and it does the true and false itself.
Yeah. Then
Oh, I see why sometimes I'm just getting minimum.
You're getting stuck in the in the loop there. Yeah. That's okay. That's not a tough fix to do. You have most of the like all the framework is set up. I think you just need to do a little bit of work on how the data is being passed between the loops. This doesn't want to move. It's making me sad. There we go. Great. I don't know why that made me so pissed off. Okay. So this is the applet. And the first thing that we do is generate a sine curve, because this is how we're modulating the voltage on the K cube. What we have here is, let's see. So we have a for loop, and what we initialize before that for loop is the sine curve. So we have a minimum and a maximum voltage that it will go to, and like a number of cycles and everything. And that goes into a file here, right? So this is a naming thing, and this is the file of the sine curve that's saved with the data. That array here specifically, I think actually comes from this loop, right? So yeah, before I go into applet, I'll talk about the sine wave generation loop. So this is idling, doing nothing most of the time, and it's waiting for you to change settings here. So if I run this, can you plug in the spectrometer actually, please, so I don't run into an error? Sweet. See if it works the first time. Ah, that's my fault. I did something dumb. Yeah, because I left this here. My bad. How dare I do that? Okay. Sweet. Okay, so basically we have this sine curve generator loop, and it's treating this sine curve as an independent function, like a function generator, but all of it is just like internal software. So it's just waiting for you to click go. So when you click sine wave generator, it will produce a sine curve there, and it will use that for modulating the voltage. So the minimum and maximum voltage is set by default over here by this. So 2.75 is the maximum voltage for one laser, and then 1.7 is for the other. It will modulate between those. We'll take 16 spectra per period. So the peak to peak number of data points is 16, and it repeats that 8 times. And that's pretty much it. So I'm gonna stop running this. I guess anytime I make a change and I click this button, it will change that. So if I just want one of these guys, then it will do that. But I will go back to 8 because we like powers of 2 here. And then I'll stop the program.
Thank you.
Of course, don't worry about the king. We know he's a problem child. So we have this sub VI that runs, and basically it takes in all the parameters that we want for the sine curve, and it spits out a 1D array of the voltages that we want to put into the K cube. So mouse is lagging. Okay. And it dumps all of that into this sine wave array over here. And this is the array that we loop through for the applet. So if we come back up here, which is where we started, we have this sine wave array. And for every value here, we're going to execute this whole frame. So we initialize a blank array, which has the size of a spectrum, but no elements in it. So it's just like a pre-allocated array. And what we do is first write to the K cube. And then we take a spectrum, which is passed in from here. So it looks like it's not really like taking data every time from here. It's just spitting it into a local variable. So this works, but you don't really have control over like explicit control over how the information is passed between loops. So I think this is like okay, but what you might run into is that one loop is running faster than another. And sometimes you may be taking the same spectrum that's in here and writing it twice to a file. Or it could be the other way around where you're actually acquiring spectra faster than you can save them. So you may be missing spectra. So this is why usually you want to do the consumer producer handshaking, because it ensures that like you're synchronized between your acquisition and saving functionalities. But this will work. This will produce the data, but that's somewhere that the functionality can be improved. The algorithm makes sense though. So we every time this executes with a different K cube voltage that's set, we write that to the display. If this is the very first spectrum that comes in, we initialize the array stack, the spectrum stack. And then if it's the second, third, fourth one, whatever, then we append it. So this is how we're building that 2D array with the applet data. So once it's looped through all of these data, it will go to the intensity chart here. So this shows you as the applet data structure is being built in real time.
Is the oscillogram?
Yes. And then the final stage here is that the data is saved. So
I was changing something here, so you can just skip the bottom part.
This guy here?
Yeah.
Yeah, no problem. But yeah, here, this is where the actual applet file is saved.
Yeah.
That's it. And then over here, data collection done. So this is a light that I guess is blinking or on when applet is running. Takes a little while, so it's nice to have that feedback from the software to let you know that it's doing something and it's not just frozen. So then once it's saved, then it goes over here. Is that the entire functionality of software?
Yeah.
Of this right now? I think I've gone through all the loops. I think that's basically how everything works. Does anybody have any technical questions about this first? And then we can move to like more broad questions about like algorithms or like data processing philosophy, if you guys want.
Yeah, I'd be interested in understanding more the consumer producer thing you were talking about.
Yeah.
Where, like, just what the best way is to do that.
Yeah. Yeah. So that would be like a good version 14 to work on, is to adjust how that works. And first, in the case of just surds, get that working first. Usually what that would entail is like probably a little bit more overhead in terms of like checking data. So I would be like counting the number of spectra that have come out of the producer loop. And then I would be like checking a condition to say like, while for Surd's case, the number of spectra that I've acquired is less than 2, I want to keep saving that. For Applid, while the number of spectra is less than, what was it, 16 times 8 there. So while it's less than 128, then I would want to continue saving spectra. There's always some sort of checking that you need to do between the two loops.
Yeah.
Sometimes it's like an LED that you use to make sure that you're synchronized between producing and consuming loop. There's a bunch of different ways to do it, but
Some checking this stuff here.
yeah.
So if it's checked like that by the number of spectra, and if it's too fast and generate two same spectra, which is not correct, and this number counting.
Yeah, so if it is acquiring spectra slower than it's saving them, then you'll have the same spectrum twice in a row.
How can you, I guess just by counting, that's the best way to know that you're running into that problem.
Yeah.
But it could save to spectra and count it, but not different spectra at the same time. Like, we didn't run into this problem so far.
No, yeah.
No, because I was checking, like, I was opening all the Excel sheet that we were saving and checking and plotting, like going through them to make sure we're saving properly until we got to 56 spectra. So I didn't run to that, but that's very good to have something to check. I didn't know about it.
Yeah, so it's probably because you're acquiring spectra for some time. Right? Like if you're taking like upwards of a second to acquire a spectrum, like this file saving loop can run like thousands of times easily in that period of time.
Yeah.
So it's about figuring out where your computational bottlenecks are. And I think since we started this project, we knew that like the amount of time that we're actually like sitting on one spectrum will probably define like the time scale of all the different operations that we're doing on it.
Yeah, cool. I can add a clock as well to see how long does it take for taking all the spectra for finding different side moves.
Okay. I'm going to stop recording then.